Hi everyone, in this video I'm going to talk about the methods of doing independent tests. Independent tests. And in this video I will talk about the methods, and then in next video I will do an example. Okay, let's start with an example, right? So let me show you why you want to do an independent test. So the question we're asking is whether the male's GPA is different than the female's GPA, right? So with male and female, and then whether their average GPAs are different. This is the question we're interested in, and this is something that we want to test. To do this, we collected N1, right? N1 means what's the sample size for male. So N1, 56, that's their average. Well, not average, but how many of them, right? So 56 of male in the sample, N1, and then their average, x1 bar equals to 3.4, and their samples estimated standard deviation, sigma 1 hat, equals to 0.8. This is the male group, and then for the female group, with N2 equals to 48, x2 bar equals to 3.6, sigma 2 hat equals to 0.6. So this group of information applies to male, and this group of information applies to female. Okay, so remember we talked about when we do testing, we actually doing testing for two populations. So this set is the male sample and this set is the female sample, but in fact this set of sample is from the male population and this set is from the female population. Okay, so we're testing these two populations, whether their average GPA is different. Okay, so as you can see, these two samples are independent, right? This group of people are not in this group. This group of people are not in this group. So the two samples are independent, and therefore we would like to do an independent test. Okay. Now let me quickly connect this back to our previous video. In our previous video, when we do graded tests, we introduce a variable mu d, right? So we were able to do the testing by taking the difference between the two samples before and after. But in this case, the mu d concept cannot be applied. For independent tests. Okay, so the mu d concept or mu d method cannot be applied here because these two samples are independent to each other, right? There's no before after, so you cannot really take a difference between them by using this concept here. Okay. Instead, we'll be using a different formula. So the test statistics that you're going to use for independent tests, the test statistics that you're going to use is observed value minus your expected value divided by your standard deviation. Okay, there's a lot to talk about here. Let me first say that expected value is the value to test. Okay, value to test. Usually what we do is when we do a testing of two populations using independent tests, we're going to say one of them is the observed And then another one is the value we want to test. And then we want to see if the observed value is different than the expected value or the value to test. Okay, we'll demonstrate more this part with an actual example, but in this video, the concept we need to focus on, or what's important to talk about, is how you would get the standard error. Okay, so I'll say standard error, right? How do you get the standard error? Okay, and in the independent test, how you would get the standard error, it's based on I would say the data you have, right? It's based on the data you have on hand, okay? And this will change how you construct your standard error. Okay, now let's focus on finding standard error. Okay. One sub-concept below standard error we need to pay really close attention to is the concept of degree of freedom. Degree of freedom. Okay, this plays a major role in calculating your standard error. Remember in our previous concept videos, when we had only one population, finding the degree of freedom was easy, right? You take your sample size minus 1. But in our case, let's say we have M1, number of male, and number of female. Which one to use, and which one to apply to get our degree of freedom? So that is the question. And for the purpose of this class, I'm going to tell you 3 ways. So we have 3 ways to deal with degree of freedom. Okay? Okay, well, 3 ways to do it. The first way is what we call the conservative method. Conservative method. Okay. So the conservative method, under this method, our degree of freedom equals to ns minus 1, where ns means the smallest sample size of the 2. ns means the smallest sample size of the 2, right? So whichever one is smaller, then you're going to use that one to subtract 1 to get your degree of freedom. And this is our conservative method. Okay, and then the second way is what we call estimate degree of freedom, right? This is the second way to determine the degree of freedom, but for the purpose of this course, we're not going to discuss in detail. Right, so I'll say this one's not for this course, because I want to focus on the 2 most common ways, the conservative method and the pooling. The third one is the pooling, the variance method. Okay, this is the pooling, the variances method, or sometimes we just call it pooling, the pooling method. The concept behind the pooling method is you're going to weight the standard error according to the sample size, right? We're going to weight the sample. Well, we're going to weight the standard error based on the sample size. Okay, right? And this is the concept behind this pooling. What's important that we have to focus on, I'll put 2 stars here. In order for us to use this pooling method, we need variances of the two populations to be the same, right? So this is a very strong condition or very strong assumption, is that in order for us to use the pooling method, the two population variances, they have to be the same, okay? We'll talk more about this, but this is what's under, it's one of the requirements of the pooling method. Okay? Hey, if we are going to use the pooling method, then the degree of freedom is okay, and the degree of freedom equals to n1 plus n2 minus 2, right? You're going to sum up the two sample sizes and divide by 2. I mean, subtract 2, yeah. And what's the benefit of this? So the benefit is we'll have a bigger sample to work with. Okay, and this is the benefit of this pooling variance. Okay, well, now I want to get back to this concept, right? As you can see, this is really hard to satisfy, right? It's just hard to find two populations and then they have the same variance. Okay, note, the pooling method can be robust. Okay, so the pooling method can be robust, and let me explain to you what does robust mean. Okay, so robust simply means that we can violate the assumptions a little bit, right? If we just violate a little bit, not too much, and the results can still be good. Okay, so this is what robust means. And then what does pooling method can be robust mean is that combine these two, all it means is it's okay to use pooling, even if the two variances are not exactly equal. Are not exactly equal. Okay, so it's okay that they're not exactly equal, but not too far apart. That's what it says, right? Because you can only deviate, you can violate a little, right? So not exactly equal is okay, but not too much. Okay, so what is too much, right? And how much you can violate. Now let's talk about the rule of thumb. Okay, so now we have two methods. One is the conservative, another one is pooling. The rule of thumb is going to tell you which method you should use. Rule of thumb. Okay, the rule of thumb, let's say, we'll use the conservative method if either of the following is true, right? So if either the following is true, then you're going to use the conservative. Yeah. First one is one of the sample variances. It's more than 4 times bigger than other sample variance. Okay, so if one of the sample variance is 4 times bigger than the other, then you're going to use the conservative method. Yeah, let me show you what it means. Okay, so we have 2 samples. We have sigma 1 hat square to get a variance, sigma 2 hat square, right? Another variance. Okay, so if Q1 hat 2, the first sample variance is bigger than 4 times sigma 2 square hat. If it's bigger than 4 times, then you're going to use the conservative. Okay, if it's not, then say in the sigma 1 hat is less than 4 times sigma 2 squared, then you're going to use pooling. But this is not done, right? You have to do it again by switching these two. So you also need to check if sigma 1 squared, right. Let me switch them. So if sigma 2 square hat, if this one's bigger than 4 times sigma 1 square hat, then we use conservative. If sigma 2 square hat is less than 4 times sigma 1 hat square, then in this case you will use pooling. Okay, so it kind of depends on what situation you are in, right? If it's greater than, then you're conservative. If both are less than, then you're going to use pooling. This one is applied to the variance, but sometimes if you have standard deviation, then this rule also applies to the standard deviation, but we need to switch something here. Okay, so this is the first one. Okay, the second one looks at the standard deviation, but what I'm going to write here is the same as the variance, but looking at the standard deviation. It's one sample, standard deviation is more than 2 times of other sample standard deviation, right? If it's 2 times, then the standard deviation. So basically, this one, you just take the square root of both sides, right? So these two are exactly the same. Usually, you only need to check one of them. So I'm gonna finish up sigma 1 hat, 2 sigma 2 hat, right? You will use the conservative with sigma 1 hat less than 2 sigma 2 hat. You're going to use pooling. Okay, but you also check the opposite. Hat greater than 2 sigma 1 hat. You use conservative. Okay, and then sigma 2 hat less than 2 sigma 1 hat. You're going to use pooling. Okay, right? So basically, you just have to look at the sample standard deviation and do a comparison. When you do the standard deviation, you're going to use 2. When you do the variance, you're going to use 4. Okay. Now, once we decided whether we're going to use pooling or conservative, then we'll be able to write our standard error. So if we do conservative, so if conservative, if with that method, we decided we're going to do conservative, your standard error is equals to sigma 1 per head divided by n1 plus sigma 2 head squared n2, right? So this is just the first sample variance divided by sample size, second sample variance divided by the second sample size, and that's your standard error. And your degree of freedom, again, is your ns minus 1. Okay. And then for pooling, yeah, let me switch to this side. Okay, for pooling, we have just an error equals to 1 square n minus 1 plus 1. Okay, I think I'll need a little bit more space. Okay, you just say an error equals to, so first variance times first sample size minus 1 plus the second sample variance times n2 minus 1, and then you're divided by n1 plus n2 minus 2. This whole thing can multiply by 1 over n1 plus 1 over n2 here. And you're going to take the whole square root, right? Okay. So it's the first sample variance times the sample size minus 1 plus the second sample variance times the second sample size minus 1 divided by the degree of freedom, which is n1 plus n2 minus 2. And this whole part is going to be multiplied by 1 over n1 plus 1 over n2. Let me write this bigger. n1 plus 1 over n2. And the degree of freedom, since we're doing pooling, is equals to n1 plus n2 minus 2. Okay? And that's how you calculate your standard error based on which case you're in. Okay, very good. So this video talks about the methods of doing independent tests. In the next video, I will discuss an example. Okay, thank you for watching. I'll see you in the next video.